We are recording. So today is Trie. Okay, let's see. Let's start from here. So not Trie, it's Trie. So Trie are special Trie, prefix Trie. You can also call them like prefix Trie. That makes searching and storing string more efficient. Tries have many practical applications such as conducting search and providing autocomplete. It is useful to know this common application so that you can easily identify when a problem can be efficiently solved using try. Be familiar with implementing from scratch a try class and its add, remove, and search method. So okay, people that just joined, you didn't miss anything. So we're just looking for definition for what is try. So corner cases, searching for a string in an empty tree. Insert an empty string into try. Okay, so a technique. Sometime pre-processing a dictionary of words given in a list into a try will improve the efficiency of searching for a word of length k. Among in word searching become OK instead of on. So using try we can do this technique where we're gonna like pre-processing a dictionary of word. So when we're like looking for a string, it's gonna be OK of k instead of n. Now we have this problem, but before to do that, there was yesterday we did this problem, merge k sort, and we solve it in a way, but the way we used to solve it, I wasn't understand it really well, and there was another suggestion is why not like why not do like all this node in a heap and then like let the heap sort it. So this Google Doc will like explain why not putting all the elements inside the heap then sorting it is not good way, and like letting the heap smaller is a better and efficient way. I will share the link. You can like guys read it later. It's really well. I learned a lot from it, and I kinda have more understanding of time complexity. I will read just part of it to make it more clear. So both solutions are gonna push or node to the heap at the end of the day. So what's the difference for like pushing just tree by tree or like one by one, or like keep the heap limited in 3 elements, or like pushing everything in same time and just let the heap doing that. So both solutions will eventually push all node into the heap. However, the key difference lies in the number of elements in the heap at any given time, which affect the time complexity of a heap operation. In a heap, the time complexity of push and pop operation is O log m, where m is the number of elements in the heap. In solution 1, the one that we did in the whiteboard, at most k elements, where k is the number of linked lists, are in the heap at any given time. So each heap operation take O log k time since you perform n heap operation in total, where n is the total number of node. The total time complexity is O n log k. In the solution 2, which we put like all the elements in the heap, all n nodes are pushed into the heap at once. So each heap operation take O log n time, since you still perform n heap operation in total. The total time complexity is O n log. So later take a look on this It's really nice to understand. Okay, try. This is topic of today. Okay, there's a lot of people. Joanne, hello, hello everyone. Hello, Makil, Leniso, Judith. Hello, Marionette, Pacman. Hello, Pascal. Hello, Paikola. I hope I didn't destroy your name. Hello, TD, Tracy, Stephen. Hello, Simanga. Hello, everyone. Okay, let's keep going. So, a trie, also known as a prefix, tree is a tree like a data structure that is used to store collection of string. Trie are used for efficient retrieval of a key in a data set of string. Let me share this if someone want read it in with me. Each node of the trie consists of multiple branches, each representing a possible character of a keys. String keys are stored in top to down manner on the basis of their prefix in a trie. All the descendants of a node have a common prefix of the string key associated with that node, and the root is associated with the empty string. Type of tries: standard tree, compressed trie, suffix trie, ternary search tree. So we're gonna just deal with standard trie. We don't need to, like, this one are not common, so just to be like aware of them, but most probably gonna be like standard trie. Okay, let's see. Okay, let's jump to a video. There's just a post about trie. Let me share it here if someone wanna take a look. It's also gonna explain trie more in detail and like how to insert to trie. And yeah, so let's watch this video. Gonna make trie more easy to understand. Okay, let me switch my screen so you can hear audio. 1 second. Application, go live. Okay, let me put more volume. And let's go.
Hey, have you noticed that if you write something in Google, it automatically suggests you what you might be looking for? Well, this thing, among with others, is based on tries. Trie is a tree-like data structure, so it has something called root, which is at the top. Yes, and
is the volume good? Everything fine? Can write in chat.
informatics,
Okay.
roots are at top. Also, every node can have something called child. Child is the node directly under its parent, and child node can also have childs. For example, the first node and second row have two childs, and if node have no childs, it's called leaf. Now, let me show you how these nodes look like inside. Every node have references to its child, and since every node represents some character and prefix, to match the node and character, we will use something called map. If you don't know what that is, imagine that you have table and each record contains character and corresponding node. Also, since the is word, but also can be prefix to there, we have to be able to decide whether this word is in our tree or whether it is just a prefix. That is why we have Boolean variable which indicates that. Let me show you how you can add words. I got here my root node and words I want to add. So let's add car. As I said before, every node represents one character of some prefix. So we split this word into characters and add to our tree prefix for every word starting with C. Inside this node, we want to add node that represents all words starting with CA. So we add A into its map and create a new node. So this new node represents prefix CA. As you probably figured out, we add to its map R character and create a new node. This node represents all words starting with car. Since we want to add this word, we set its indicator to true. Let's try to add done. So, once again, we start at root and look at its table and see that we don't have any node representing the prefix. So we create one and add new record to root's map. In this new node, we look for O. Since there is no O in our table, we add it and create a new node which represents do prefix. In this node, we continue with N, where the same thing happens as we create new node for done prefix. In this node, we add E and once again create new node. And since we have no other characters in done, we set this node's word indicator to true and we are done. Let's try to add try. Once again, we look at root and try to find T in its map. But T isn't there, so we create new record for T and add to it corresponding node. We move to this node and continue with next character, in this case R. Since this node map is empty, we add there R and create new node representing TR prefix. And we add to this node Y record. And once again, we create corresponding new node. This node represents prefix try, and since this is the word we want to add, we set its word indicator to true. Now, let's add cat to our tree. So we look at root, but we find out that C is already in our roots table. So we move to node representing C prefix. And in this node's table, we look for A. A is already there, so we move to corresponding node. In this case, we look for T, and we find out that T is not in our node. So we add T and create new node. And because we have no other characters in cat, we set the word indicator to true. Let's add try. We look at root's table and find out record T is already there. We continue with corresponding node. In this node, we find R and move to node representing TR prefix. Now we look at I in this node. Since it's not there, we create new record for I and new node for try prefix. Since we still have one character left, we create new record for E and new corresponding node. In this node, we set the is word indicator to true. Let's add our last word, do. We look at root and see that D is already in the table, so we follow its pointer. Now we try to find O in this node. O is in this node, so once again we follow its pointer. Since we have no other characters to follow, we set the is word indicator of this node to true. Let's try to find some words. First word is CA. Remember, each node represents prefix, so we start at root and look for prefix C. We follow C's pointer, and in this node's table, we are trying to find A, because in order to find CA, we need to find CA prefix. A is in table, so we follow its pointer, and get the node which represents CA prefix. So we look at its word indicator, and since it is false, this word is not in our tree, even though...
Okay. So CA. So why it's not in tree? Oh, you can explain this. Why CA is not in tree? Okay, let's see. So let's keep going. Maybe we understand it. Why it's not in tree?
We found corresponding prefix. Let's try to find zebra indicator, and since it is false, this word is not in our tree, even though we found corresponding prefix.
Okay, so this is a prefix. So in here, let's jump to a note that is important is like, notice here there is false, true, true, false, true. So why do you mark this? So marking the end of a word, marking the end of a word in a tree data structure is important for a couple of reasons. Word boundary. It helps to distinguish between a word and a prefix. For example, if you insert the word apple and up into the trie, marking the end of the word allow you to distinguish between the complete word up and the prefix up in apple. A word existence. It allows you to check if a word exists in the trie. When you search for a word, you traverse the trie according to the character in the word. If you search a node where his word is true, you know that the word exists in the trie. If you reach a node where his word is false, or if you can't traverse the trie according to word character, you know that the word doesn't exist. Okay, who's still confused? Maybe we can explain it in Escalidra. Yeah, it's like null terminate and you get end of string. But it's tricky a bit. So like for example, I put apple, or like let's say apple. So this is our node. Let's say this is the root node, and then we insert a new word, apple. Okay, apple. Okay. Okay, we have apple here. Now when I'm gonna search in this node about word apple, I'm gonna be like, okay, p, okay, it is true, it exists, right? True, apple exists. Now I'm gonna search about word up. I will be okay, go to the first one, up, pop, it exists, it's true. But now here's the confusing part. We never insert up. We never insert the word up in this dictionary or tree. The up here is a prefix of apple. So we need a way to distinguish between them. So if I insert apple, and they said, okay, search for up, it should like return false. When I'm gonna say research for up, it should say false, because I never insert up in the tree. This one is like a prefix of apple. So here where the marker come to play the role. So I will mark each word I insert. So for example, I insert apple, I'm gonna mark this. Let's say this is a mark, right? Like a boolean in this node. Now I'm gonna search apple, APPL. Okay, I found it. Does it have the last character? Does it have a mark? Yes. Okay, so this is a word, valid word. I return true. I'm gonna search for up. P. Is it have a mark? No. So that means this is just a prefix. I never insert a up word. So here I return false because it doesn't have a prefix. It will be more clear when we're gonna jump to a second video, I believe. Okay, let's. Anyone have question? Like, don't feel shy.
Okay, so good evening.
Yes.
So what are we looping through? Is this a search algorithm?
This is a node. You can say like a node list. This is a tree, like a tree. It have a root, next node to it, like next node. You know, like a tree.
Yeah, but so to answer your question, yeah, it is a search algorithm essentially, right? It's a more efficient way of storing something like a dictionary. In this particular case, we're using words. So imagine trying to do it without this, and you have a list of words that you need to quickly search through. it would probably take a certain amount of time and complexity. But this is a way more efficient way they've found of not only storing a dictionary of words, but then retrieving the words.
Can you please go over it over and over again? I'm kind of confused. Why is app true and then app is fail?
Oh, why is app is false, right?
Yeah.
Okay,
Why is
let's
one app true and then the other false?
okay, let's see it again. So, let's say we have a dictionary right here, and I write apple. Oops, this is very small. Okay, let's say I write apple here. Okay, here's apple. Can see it? Okay, so now if I go here and I search about apple, it should be true. But if I search about the word up, it should be false, right? Because there is only apple here. But if I insert here word up, it's gonna be true. This should be true because up exists. Now I also can search for like prefix, right? For like if I go to here and I search for a prefix of up, it's here because this is a prefix of apple, so it should be true. But if I search for word up, this should not give me true because this is word apple, this is word up. Is it clear? Like why it should give false when we don't answer it?
Okay, so I understand. Sorry, I understand how the algorithm works now. The only thing I'm curious about is how do we mark each word where we want them to stop? So, for instance, let's say I have apple in the data, just like you explained.
Yes.
And of course, I'll put a marker at the end of the E that makes apple. I get that correctly. My question here is, how do we really, when we are implementing, how do we create a marker at the end of the word?
So
what type of marker do we do?
So for example, if this a node, for example, if you go back right here, so this is a node, right? So in node you can put anything you want. Like notice here, headed boolean is a word, and he declare children here, like chain of character, like maybe array of character. We are free to set up our node as we want. We can like do, for example, a hash map, like a dictionary. Maybe our node is gonna be like this node, and inside it we can do a dictionary, right? Dictionary. Okay, and here we can do like end of word, for example, end of word, or like let's say end, and we give it like false or true. So every time I create a new node, it have this what the right word for it? Attribute. It have this attribute or parameter.
Okay, so I get you. It is more like some sort of structure that has a node, and within the node we have the object detail, and then inside that same node we have an object that signifies an end for it.
Yes.
Exactly.
Yeah, it's like a linked list. We have like next.
Exactly.
Yes.
Exactly. But what language would you be writing this in?
Can you repeat?
So what language will you be writing this? Is it in Python or in C?
Yeah, Python.
Or what?
Python.
Python. Okay,
But you are free to like solve. So in Lit code you can solve the problem with any language, right? Why Python is because it's more simple. and it's more faster. But you are free to do it with any language. So let's go back to our topic. So now I believe everyone have idea why this marker is important. Later in when we're gonna maybe go to solving this problem, it's gonna be more clear. Please, if you have question, don't be shy. You can just open mic and talk, or write in chat, and we read your question.
I don't have a question, but I have like kind of repeating what you said to be sure. You said if it's a word, then apple will equals true, but if it's a prefix, then apple will be false. But then how do we know if a word is a prefix or if a sentence is a prefix or a word?
Okay, so I think you are thinking about it from a bit different way. So when we say true and false, the question is like, is this word exist in the dictionary, right? So if we say, is up word exist in dictionary, and I'm gonna go here, one, okay, the first character exists. Let's see, p exists. Okay, nice, we're going p. Oh, up exists in dictionary, but wait a second, this is a part of apple, not the word itself. How did I know that? Because when I go to this node, I find that it doesn't have a marker, so I understand that it's part of another word. You know what I mean? Then I would be okay, it doesn't exist in dictionary. But if I was going in dictionary, a exists, okay, next character p exists, okay, p, oh, it have marker. Okay, that means someone insert this word in this dictionary. That means up itself exists. Is it clear? Stefan?
It is clear, but I kind of processing why someone would do that.
Oh, so how? Because if we didn't do this marker, we're not gonna know. We're not gonna know.
Because you're finding a word up, and then if you're searching for app, then and then you want the word apple, so it shouldn't like print as apple, but it should pop out app because it talks something about Google search.
Yeah, but like imagine you have a database of million word, right? And you are searching. You said, okay, can you search in database if app word? And it say yes, it exists. And then when it show you the results, what did you find? You found apple. Is that what you did search for? You didn't search for apple, you search for app. So there is a problem in your algorithm. You know what I mean?
Like when you're dealing with false positives, because you could be trying to.
Yeah, go ahead, Pacman.
Members of this chat, yeah. Like if you're trying to find all the members who attended this PLD, let's say you have someone called Bernard, and then someone called Ben says they attended the meeting. So you just try to search to see if Ben actually attended the meeting. So if you don't have an actual marker to say that there's a key called Ben and it's actually a complete word, you would not be able to determine whether or not it's a false positive. So you would be able, if Bernard was there and you didn't have the marker, you would go through BEN and you'd be like, okay, so does that mean Ben was there? So if we didn't have that marker at N, then that would be a false positive. So we're trying to take care of that. And then, so this is like another reason, something that Nyangasi had picked up on was how it actually improves the performance of your search operation. Because if you were trying to create an index of everyone who attended this meeting, for example, you could maybe use something like a hash map, which would be like an index which has numbers, which is like an array 0 to 10. And then for each number, you'd have the member name, right? So 0 would be Ben. Number 1 would be Bernard. Number 2 would be Nyangasi. Number 3 would be someone else. So in that case, you'd be searching. It's still efficient because you should be having an O lookup time of a hash map, which is like O of 1. But when you transition from a hash map to a trie, I guess it improves because you're only storing the letter of the alphabet themselves. So you would have the same number of keys to search for Ben as you would have to search for Bernard, right? Because they are all consisting of the same letters, so you're not really wasting space to store duplicate values or duplicate letters. Yeah, so the space complexity, I guess, decreases by a significant amount.
Yeah,
I think this is what,
Just
if you remember the MySQL with the indexing, I think indexing does something similar to this.
Yeah, this is actually
a particular
like
column.
And if you look at the Wikipedia link for tries, you will see that it's used mostly in searching and natural language processing, which is like creating tokens out of words to improve how you can recognize common words in English. So if you can recognize using the tries, it becomes way easier to find out what the word is and which words are related to each other.
Thank you. Thank you, Pokemon.
So that makes sense. It's too quiet.
I think it makes sense. Who have more question or addition? Anyone?
I just wanted, I think probably just to make an addition. When you search, as he explained using the example of Google, when you search for an app and then it brings up Apple application, those words, they have a marker at the end. In this, using this example which we've used, those words for them to appear there, they have the marker at the end. So despite the fact that they are prefixes, they appear as options for the search because they have a marker at the end. So that's the reason for adding the marker at the end of a word. So as much as it might be a prefix to another word, but as long as it has a marker, it appears when you do the search among the options which are presented. So I think probably it's the guy you explained earlier made it a bit more clear. So I think it should be clear now.
Thank you. So here we are saving time, saving space, I guess, right? So that's what, because otherwise we're gonna have another A here, another A, B here, right? We're gonna have two words. So now we don't need this, like, just to save this, to create this space. We can use this already there, and just use marker. What if we have word apps? Now, this one Apple have L here, doesn't have S. So, what we should do? Do we create Apple and apps? What do you think?
We need to create
you need to add
another node after
P here?
the second P. Yeah.
Yes.
Okay, and probably mark it.
And then mark through. Yeah.
Okay, that makes sense. At least I hope everyone like following with us. Like there's no question. If you have question, please don't, because when we're gonna go to problem, it's gonna be hard to understand if you don't understand why marker and how we add nodes. Okay, let's keep going the video. Where we were? Here. Okay, now let's see this.
And in this node table, we are trying to find A, because in order to find CA, we need to find CA prefix. A is in table, so we follow its pointer and get to node which represents CA prefix. So we look at its word indicator, and since it is false, this word is not in our tree, even though...
Okay, now why CA is false? It's here, this word, why it doesn't exist? I guess now we know why, right? Because this is not a word, this is prefix of car. Okay, let's keep going.
So we found corresponding prefix. Let's try to find zebra. So we look at roots table and look for Z. Since Z is not in there, there's no way that zebra is in this tree. Actually, because Z is not in root.
Here, if you notice, the implementation of the node is a bit different. He didn't use like he did like car, like air itself. It have true here, so it's like he add a new node that's at the end of the word, not inside the node itself. Interesting.
We can say that any word starting with Z is not in this tree. Let's find try. In this roots table,
Okay, this zebra is not in tree because in the first level of the linked list, or like the tree, we don't have Z. So automatically it's not in tree.
we found T.
Yes, Emmanuel, if you can mute your mic, please. Thank you. Okay, so
record. So we follow its pointer. In this node, we continue with R. Since R is in this node's table, we follow its pointer and get to node which represents TR prefix. In this node, we look for last character I. I is in this table, so we follow its pointer. And since we have no other characters left in our word, we look at this node's isWord indicator. Since it is true, we can say that try is in this tree. Let's try.
This technique is also good. Like he's using the null pointer. So here he's using like a null pointer, or at like a node that is have true. True. So let's say this is the end of the no, it's not null pointer. The end of the word is gonna add the true node here. This have value true. This gonna add a new true here. But this approach is like inside the node you're gonna like have two attributes, or like I forget the name of them.
To find card. We started root and follow C. Then we follow A. We still have two characters to go, so we continue with R. We get to node which represents card prefix and look for D in its table. Since it is not there, card is not in this tree. Let's try to delete some words. In order to delete a word, we need to find it. If this node have child nodes, we cannot delete it. So we just set the isWord indicator to false. But if this node have no childs, we can delete it and then check if we can also delete the nodes above. So let's delete do. We look up do and see that the node representing do prefix have child. So we just set the isWord indicator to false.
Oh, that's cool trick. I didn't think about this. So if you want to delete some word, you just switch. So if in our case we want to delete this up word, well, I'm gonna go to the it and I'm gonna just turn off this to false. Okay.
Now let's delete try. We look up try and see that this is a leaf. In other words, it has no child. So we delete it and also delete the record that points to this node in node above. Now we see that the node above also have no child nodes, so we can remove it too. And once again, we also remove the reference in node above. Now we try to delete node above, but it have a child, so we cannot delete it. That means we are done. Let's try to delete CA. We look up CA and see that the isWord indicator of this prefix is false, and we cannot delete something that is not in the tree. So we are done.
Okay. The last part is very nice. So if the word that you're gonna delete have more, or like it's part of some other word, you skip it. But if it was like, let's say up is not here and there's only apple, if I want to delete it, I'm gonna check the last word have only check mark and there's no more words she's not like this word not part of any word, I can delete it then. Or if it was up exist, I will delete just this two nodes. I will stop here because this up is used from this second word. So I will delete just L and E. Interesting. Okay, let's jump to the second video. Is shorter than this one. Is this one gonna just show us another approach to it? They are the same concept. It's just the approach is a bit different.
This is the programming book lady.
Yeah. What's called that book? Cracking the code or something?
Yeah, it's right behind. It's the last one or the first one.
Yeah, Cracking Code Interview.
I'm Gail Locke-McDowell, author of Cracking the Coding Interview. Today I'm going to talk about tries. This isn't something CS students might have spent that much time on in school, but it's really, really important for interviews. A trie is a data structure that is actually a type of tree, but it's often used to store characters. And the way that it works is each node might store just a character as its data. But then if we look at the path...
Yes, let me try. Okay, I hope this better.
Down to that node, the tree that node is really representing a word or a part of a word. And so what it allows us to do is very quick lookups of a particular kind. So for example, suppose we use this trie to store this very small version of the English language. We could use it to say, hey, are there any words that start with CAR? Yes, there are. There's car, that's actually a complete word, but there's also card. So car is also a prefix. So it allows us to do very fast lookups. So let's talk briefly about the implementation of it. So we're gonna need a class node, and then rather than having, as we would in a binary search tree, a pointer to the left and right node, instead we have some sort of either array of all the children, or more likely some sort of lookup table that maps from a character to that node. So we can immediately say, do you have a child that is an A? Great, give me that immediately. Additionally, we need to understand not just is there do you have an R as a child, an R node as a child, but is that actually a complete word or is it just a prefix? And so in addition to each node having a mapping of from character to node, each node also has some sort of flag in it called something like is complete word that represents, is that a complete word or not? We see tries in a lot of problems. So if you're in an interview and you get a question that has some sort of word validation to it, so, check if this is, walk through this table and find all the, walk through this Scrabble board and find all the words, or given this list of strings, find all the celebrity names. So when you see something that has some sort of word list validation, think about whether or not a trie might be useful. There's one optimization that often comes up in trie problems. Suppose you had a situation where a user was typing a word, and as soon as the word became clearly was going to be an invalid word, you want to say underline it. So someone types C and you say, yes, that is in fact potentially going to be a valid word. And then someone types CA, okay, great, we're looking good. Now they type CAL, yes, okay, there's words that start with CAL. Now they type CALP, oops, no, that's an error. So that's a good case to use a trie. Now the way that I've explained trie so far, you would do each of these lookups from scratch. You'd say, is there a C? Is a valid prefix? Yes, there is. And then you do, is CA a valid prefix? And you'd start from scratch over at the root. Now, in a lot of cases, though, we actually want these calls to kind of build on each other. So one thing we can do with our trie is we can keep state in various ways. So when we look up, is C a valid prefix? We actually store where we are in the tree. So when the user types the very next character in A, we just look immediately, is A a child rather of C? Of that last lookup, rather than starting from scratch. And there's different ways you can actually implement that. One way you can do it is to actually keep state within the trie. Another way you could do that is actually return the node back to the caller. So when I say, is C a valid prefix? I get not only that it's a valid prefix, but I also get information that gives me exact reference to that node. Then, rather than starting from the root and saying, is CA a valid prefix? I just ask, is A a child of C? And then I ask, is L a child of the CA? Et cetera, et cetera. So again, tries are not something that you would spend a lot of time in algorithms classes or in an algorithms textbook. And so they're unfamiliar to some people. But it's a very, very common data structure for a lot of interview questions. So keep an eye out for that, construct or that frame of a problem that says something about, validation of words, because that's often where we're going to want to use a trie. So now that you've understood the basics of a trie, why don't you try applying this to a new problem? Good luck.
Okay, that's what we're gonna do. How did you know? Let's go apply this. We are now professional trie programmer. We understand trie very well. Everyone here, 24 people, everyone understand trie. Let's jump to let's code. Let's try this with trie. Okay, so let me share screen. Okay, how we gonna do this? Give me your idea, guys. Don't be shy. We know now trie. We know how it works. Let's read the first problem. First of all, let's ask, anyone have a question like why or like how, like something not clear yet in trie? Any question? Please go ahead. Okay, so the first problem we have is implement trie, prefix tree. And if we go see, where is it? If we go see the code, so we're gonna create like a class tree that have in its insert search starts with. So we're gonna insert in the trie, gonna search on it, gonna return a boolean. We're gonna start with, like, this is gonna check prefix if it starts with, if this prefix exists in our tree. Also boolean. Okay, let's read the problem. A trie, pronounced as trie or prefix tree, is a tree data structure used. Let me refresh this page. Okay, why it does not show everything? Used to efficiently store and retrieve keys in a data set of string. There are various applications of this data structure, such as autocomplete and spell checker. By the way, you can see my stream, right? Okay. Implements the trie class. Trie initialize the tree object. Okay, we have that here. Class here. Void insert. It's gonna insert the string word into trie. Okay, we should build this method. Boolean search, return true if string word in trie. Search here. Example was inserted before and false otherwise. Start with return true if there a previously inserted string word that has the prefix, and false otherwise. Okay, so this one starts with is, for example, if we insert apple and I did do up on starts with, it should be true, right? Because starts with is a prefix of apple. So basically starts with, let me remove this, starts with, I'm gonna give it up. It's gonna look if there is any word that have the prefix apple. So actually here we can like not care about anything, right? We can just start from the level 1 of the tree. Is there up? Yes, it is. Level 2, is there P? Yes, it is P. Is it another P? Yes. And they will return false. Like, I don't care if there's a mark, if there's no mark, right? Because if up is a word, that still mean up is a prefix of up, right? It's prefix of itself. It still give us true. So we don't care about the mark, I guess, here. This search starts with gonna be just searching. Any idea how we can do insert? Or like maybe we take this problem. Okay, let's see the input. We did so this input is confusing, but this is just a way how to control this method. So first of all, we call a try, like here. We create a new object try with nothing, no parameters. And the second one we call the method insert, which is this one. We give it parameter apple, right? So is this gonna return something? No, null. Also this return null, right? Now we call try search. We give it parameter apple. Here is it, input. We call method search. Did we give it parameter? Yes. So this second array is like parameters for this method. This is just so it can be easy for us to add a new test case. For example, I want to do this test case. If I want to do another one, I can say like insert ups, search for up. So to control this test cases, this is the way in Let's Code. Now when we did search on apple, it's returned true. So search apple, it give us true because we did insert apple before. When we did search for up, it give us false because we didn't insert any word up. We did only insert apple. But when we did start with up, it give us true because there is a word apple that starts with up. So this prefix exists in our tree. Then we insert up itself. When we did search up, it give us true. Is the problem clear? Any question? I think it's straightforward, but if it's not clear, please go ahead. Okay. Silence, that means it's clear, right? Okay, let's see how we can do this.
It's clear for me.
Maybe we... Can you repeat? We take this right here. And we design everything here. Someone said something, I didn't hear you. It's clear? Okay. Okay, that's good. So this is our case. Now we're gonna first we need to create a node, right? So we're gonna create a node. Now this node have a root, and we're gonna start inserting each character. So when we're gonna do insert, we're gonna insert, for example, apple. We're gonna add apple here, character first, and this node we're gonna also insert another. When we're gonna loop through this string, we're gonna insert another character, the second character of it in the node. So a b b. So we're gonna keep looping through this string and adding it as a node. And the last character, E. And let's say our data structure of this node, we have Boolean. Let's call it end. Let's call it end. We give it false. False. And we can do, how we gonna put this we can use hash table, right? A hash table, for example. So each node, because so this node we insert A, it have children, right? So this is the children of this, and this node right here, it have children. So this is children of this, and it keep going. This is children of this. So each node, it have some data saved inside. So I can do hash table, and for example, A, it's gonna have P. It's gonna have P L E inside A, and P, it's gonna have just this one. L, it's gonna have just this one. Any idea? So hash table, or like call it children. Children. And this gonna be a hash table, right? So I'm gonna just do this like a hash table.
Yeah, I think the hash table is best, yeah.
So now we have the structure of our node. So each node is have this property or like attribute. Okay. So what we're gonna do? We said we're gonna loop on each string and we're gonna keep inserting node. Okay, let's do that. Let's do pseudocode of that. How is this gonna be? When I write it, it's so small. Maybe I should make this smaller and zoom. Okay, let's jump in. Oh god. What the hell? Okay. Maybe we can... Oh. Nice. Okay. So, what we do? Create a node right here. What do we call it? Create a node or like tree. I don't know. Create a linked list. Create root. Create a root. Let's create a root. I think I saw them. They say root. Okay, we create a root. It's empty. It have nothing. Now we're gonna insert. So this is insert. Insert's gonna start here. How are we gonna insert? What is our logic to insert? Okay. Oh, we're gonna insert. Let's start from beginning. So we're gonna loop. Okay, so we need to loop because they're gonna give us apple. So of course we're gonna loop on string. Let's start from here. Okay, we're gonna insert something. So what we're gonna insert? The word. Okay, so loop on each character of string or word come on. Okay, we are looping on each character, and then what we are doing, so let's say I'm loop on A. What I'm gonna do to A, I need to create a new node and somehow link it to the root. Okay, let's not care about technical now. Let's just say create. Okay, each character, loop in each car, add it as a node. But how do I know which node I'm gonna add it? So
I think the root, since the root is similar to the root class is similar to all the other nodes, that means it will have children also.
Oh.
So
wait, repeat that, please.
That children array will now be the root node will be similar to all the other nodes.
Yes, yeah,
you can't use a different node now.
Yeah.
Yes, so it will have this children dictionary there.
Yes, it's gonna have
so maybe we can put in a what's it called? A key that shows roots, and then the root is pointing to the first node. So that first node will be a child of the roots.
Okay, I think I get you. So, but the roots is already have this apple, or it should supposed to be. So like in the start, it's gonna be empty, right?
Hold the whole.
It's gonna be. Can you repeat, please?
I'm saying like the root will hold every child of each.
Oh, we're gonna add them to the dictionary of the roots. Now I get you.
Yeah, that's what I'm saying.
Okay. So now we loop on each character A. Now we need to add this to the root of children. Okay, thank you. That's made more sense now. So we loop on each character of word, then. Oh, wait a second. What if that's. So how are we gonna do it? Because we only need to add the first character to the root. Because the second one it should be in A.
The next character to the first. Okay.
Because when we're gonna. Okay, this is more challenging than I thought. So we need to add
something like a linked list.
Yeah.
Can I say something?
Yes, please go ahead. Yes, please go ahead.
Okay. So I think the root node is going to be a dictionary, and every single alphabet that would ever exist, like A, B to Z is going to be a key.
Yes.
Going to be a key. Sorry for that. It's going to be a key, and like the alphabet A is going to be a key.
Yes.
That is pointing to a dictionary also. And that dictionary it is pointing to is going to also contain from A to Z also, like every single dictionary, every single sub-dictionary is going to contain a sub-dictionary.
Oh, okay. So when I'm gonna add A, the next time I'm gonna add B2 inside A.
Yes.
So I need like a pointer or something that will keep moving. So first I'm adding here. The next loop I should add a hair. Next loop I should add hair. So I need a pointer. Okay, that's
so the first thing we might have to do in our init method is to create a pointer like self dot a particular, you can call it root, self dot root should be a dictionary, and that dictionary is going to be like the parent dictionary that will contain every other dictionary. So that's what we might be assessing whenever we want to have to insert in the init method.
Like in the first time we add in the root, and
when it is being initialized, being initialized in the method, we create self.root equal a dictionary. It's going to be empty. It's going to be empty, not going to contain anything. Well, whenever the insert method is called, so we go there, we check if the first letter of the word exists in the root method, in the root dictionary. If it doesn't exist, we insert it as a key and give it a dictionary.
Oh, okay. So let's call this as a root. Let's call this as a root, and let me know if I didn't understand you correctly.
Or dictionary of dictionaries.
Yeah.
So let's try to write it in pseudocode so we don't stuck in technical way. So root. So you said like first check if the character, or like loop on each character, right? And check if car exists in children of the root, right?
Yeah, let's just say in the parent, yes, in the children of the children.
Exist
it's among the children of the parent.
Current children. Because we're gonna keep moving. Yeah. So the current's gonna be changing. Current children. Okay, and the first time the current current equal roots. Let's not go in detail. So current's gonna be pointing the root. Okay, here is it.
Yeah.
Pointing the root. Now loop on each character. Okay, apple, first character A. Check if character. Check if car exists in children. Okay, so car
current in the current node,
children,
which is the root at this point,
which is this one.
Current.children.
Current.children. Okay, that will make it more clear. Okay, so let's slow down a bit. So we have current equal root is pointing on the root. Now I'm looping on each character. I am in A, and then I will check if character A exists in current children. So I go to children of the root. I didn't find it because we just start. Dictionary is empty. What are you supposed to do? Add it, right? Add the A. Right? I should add it, but I need to add it in as a node itself because I need to add a node. So like create a root node here. Create character node.
Yeah.
Create character node. Now what we have A. What happened here?
Yeah.
I have A that I just create from this code, from this line. Okay, now we created. Now we're gonna loop to second one, but this time I shouldn't compare with the root. I need to compare with the next one.
Yeah, change the current root to the.
How we can change this? Change this to this. So maybe after we create a node, we can move
current equal.
Say that you see me.
Create character. Okay, let's say create character node equal character node. Character node that we added. Remove this that we added. So current's gonna be here.
I think we haven't added the node to the root child or the root children dictionary. We only created the node.
Yes, maybe, and add it to current.
The current children.
Okay.
Can you mute that person?
Yes. Oh, have someone. Peter, can you like mute your mic, please? I mute you temporarily until like you. Okay, so now what's happening? Now we have current character node that we added. It's here. Now we are gonna loop on P. We did loop in P. Oh no, we move the current, right? We create current, then we're gonna loop. Then we're gonna loop again. Second character, P. Now I'm gonna go check if the character exists in current children. So this current children we just added, it's empty. Like the children empty, doesn't exist. Create character node and add it to the current. So this one, I'm gonna create P. I'm gonna combine them, add them. Now current, I'm gonna move this pointer. Current's gonna be character node that we add. So this gonna move here. Okay, so far it's working. We're looping again. Moving to P. Now again, check if character exists. It doesn't exist. It's gonna add it. It's gonna link it. This gonna move here. L exists, doesn't exist. It's gonna add it right here. Okay, it's gonna add it. This gonna move down. Then again we're gonna loop other time. Our string is not finished. We're gonna add it right here. Now we're gonna move our current here. Okay, now we can do another loop because this is the last character in our string. Now we missing something, that's the mark, right? Because we need to turn this. We're gonna add it. Okay, let's say E. We jump to E. It's gonna check if character exists current children. It's not gonna find it in L, right? It's gonna create character node and add it to the current. Okay, it creates E and it's added to the current. But when it's created, this false should be true.
That might be after the loop, at the end of the loop, when we're outside the loop.
Oh, because we have access to the current. So we can come back to the current here after the loop.
Yes, and see how.
Yes, we can do it here. So, because in this loop, we're looping, just adding. But after the loop finish, we can just do current children. No, not children, end. We call it end. True. Now this node right here, it have the mark. It have the mark true. So now we add all the string to the try, and it have the mark. Maybe this gonna work. We can try it, but probably should finish all of this. Then we try them all. Or we can wait. We have insert here. Okay, we can. Well, no, not gonna work. We need to do them all so it checker work. Okay, let's revise. Insert. It makes sense for me. I think it's good. If someone have question, something not clear.
with the way we are implementing, it looks like we'll have to create a node class. Like the node is supposed to be a class that has the attribute end, the attribute children, so we can use it that way. If we have it like a dictionary, it might be somehow difficult to add those attributes in a single dictionary. In a dictionary, it's just a key pair value. It's just a key value pair. Do we have to create a class node?
We can either create it here.
Okay.
Can we? Or like we have to create a new node. Like we can create a new node like class.
New class, yes.
Node. Hash map dictionary and self end. False.
Wow.
Or we can do them here. Inside the tree itself.
Okay.
No, maybe not.
Maybe not, yeah, because it's going to be a node.
I mean, if we did it here, we're gonna call. We're gonna. If we wanna, I think this one gonna make it easy because we can just do node.
Yes.
Node like this to declare a node, and this is gonna be our node.
Yes.
Okay. Now this is our answer. Now let's see a search. Now the search, how it's gonna work. Okay, let's create another pseudocode. Here's it. Node A P P L E. So A P P L
I'm thinking the search will be easier than insert because you will loop. You will use the same logic. You will loop, but this case, if it doesn't exist, you return false. If the loop finishes, you return true.
Oh. Okay, so repeat. It's gonna loop through this. If it's finished, it's true.
The last word, the attribute in for the last word must be set to true. Because if it is not set to true, that means that what you just found is a sub. Is part of another word that wasn't said. Yes, the prefix to another word that wasn't said. So the last letter
in the search for prefix, but you check for also the end in this case if it's search. Am I getting it right? Because there is two methods they want to search and search for prefix, I guess.
There's one, the search for the start bit. We won't check for the end attribute.
Yeah, if the loop finished and you have the current end, you check for the current end. If the loop finished and you manage to check for the current end, you actually return true. If it's at any point couldn't finished, you return false. And if the current end is false, you return false.
Yeah.
Okay, how are we gonna do it? Sorry, I was focused with this beautiful design.
Wow, yeah.
Okay, so
we are going to check if the letter A is a key in the dictionary of the current.
We're gonna what? Check in the current?
Yes, we are going to check when we have the Yes, we are going to have when we get into this thing, the class, we will have the attribute. We have the attribute that contains the children.
So I guess the first step is also gonna be looping on the word, right?
Yes.
So let's start from beginning. So loop on each character of the word. Okay, we're looping through it. We have which word? Let's say they give us apple, right? Search apple. Okay, we are starting we are here in apple. We are here. A, what we gonna do now? We are here. What we gonna do?
We are going to go through the children.
Children
Of node.children.
Node.children.
The children of current. We are going to initialize the current to node.children.
Okay.
Before the loop.
The current.
Before the loop.
Before the loop. Okay,
yeah,
so here. Current's gonna be children. It should be should be a root.
Yeah, root.children. It should be root.children because the root itself is a node.
Children.
Yes.
Okay, root.children. But why is that? Why root.children?
Because the way we created it, we created it to have a children attribute. And that children attribute is a dictionary. And that is the dictionary will be checking if the letters are there inside are keys in that dictionary.
Okay, so I see. So root.children because children is gonna have all this character.
Yes, a dictionary, yes.
For the roots it's gonna be just the first line, like just the first. So it's gonna be just A. If we did find A, we're gonna continue. If we didn't find A, we're not gonna continue, right? Because if this children doesn't have A, there's no need to check for B.
Yeah.
Okay, so how we can do this? Loop on each character, check if character in let's call this children. In children, current children. Wait, let me make this bigger. Okay, we did check. It's gonna be true or false. So if it was true, or let's go false. Let's say false. False. Case of the false. What we should do? If it is false,
we have to return false.
Return false, right? Okay, it's return boolean. This search, it should return boolean, and this said here, return true if string word is in tree, false it otherwise. So this gonna if it is false, gonna be return false. Now, if it is true, that means we found first character of A. I guess we move this pointer group. I guess we move this pointer here, so when we loop, we check if B exists in A.
If it exists in A, we are going to assign the children to the value of the A key. Like A is going to be a key, and whatever it is value, the value is going to be a node. So we are going to assign children to that node, and that node is going to also have, that node itself is going to be from an instance of the node class. So it's going to have children, node.children. So we are going to assign the children to node.children, which will be the next dictionary we'll be checking in the next loop.
No, but how are we gonna do it from if it's true?
If true, children equal, yes, because we are checking children equal
current children, you mean?
The variable we are going to be looping, you said loop on each character of the word.
Check if character in current children.
In current children. So current children is going to be yes,
so this is current children, this pointer right here.
Yes.
It's gonna go down here.
That's mean.
That's mean. Yes.
Yes. And the key, you know that A is a key, and the value it is pointing to is an instance of the node. So we are going to access A, then get the node it points to, which is good. Then we are
so current children. Okay, this is a very bad pseudocode. That's why it's causing this problem.
Okay.
So let's say current. Let's not call this current children. Let's call it node.
Yes, node. It's going to make more sense.
Because this is a node.
Yes.
And it have root children.
Yeah.
And check if character in current children is gonna be check if character in node that children. Not that children. So maybe this should be just root. So like this is gonna be more. So this is node. It's gonna be pointing in root. Now I'm gonna loop in each character. Check if the character in the node, which is this one, children. If it is false, return false. If it is true, now the node should move. This node right here should become here. Now it's gonna become node equal node children character, right?
Yes.
Because this node that I am in pointing, it have children, and we know that A exists because it gives us true. That means A is inside the hash table children. That means I can access it. Access it. If I access it, I know it's also it's gonna have children and like the same structure of the or not. Yeah. Okay, Mike, more clear now. Please, if someone have a question, we can like explain this more or different way. Okay, so what's the next in this search? Now we have false, true. We said if it is true, it's gonna be not equal not children car. What this mean right here? This basically gonna move this pointer right here to here. Right here, because not children car from the root is this one.
Yes.
Second, please I need explanation of the second condition true. Okay, so let's say this is the root, right? Root. Inside this root, we have this. We copy it. Inside this root, we have this. And we check if inside children there is A, and it's said true. There is A. Now inside this A itself, this A itself, if I it's like a node. This A, it's like this A, right? This is the key A, and wait, let me see. Yeah. So when we add it, yeah, when we add it here, we add it like a key A and node, the node itself, the node. So basically this key A, if I find it, I can access the node, and this node, it also have children and end, and inside the children it's gonna be have P, and this P is also a node that have P, another P, and this P also a node. So it's like a recursion, like each node inside each node inside each node inside these children. So basically, going back to this condition, why we did this condition, because we are checking if this character A right here in not children of R. That means is it exist in this level? If it exists, that means it's true. If it exists, what I should do? I should move cursor to P, right? But when I'm looking for P, is I'm gonna look here in this level or in this level? I need to look in the second level. So I don't need to, I don't want to look in the root. I need somehow to access these children that I already found here, and then search in its hash table. Like each node have its own children hash table. Now I'm gonna access this by this. I'm gonna do node, which in our case it's node equal root. We just started. And then I'm gonna do dot children, which means this node root have attribute children. I'm gonna access it, and then I'm gonna do this bracket. So this bracket, because this children is dictionary, I can access the keys of dictionary by this bracket. Now I need to know A. I'm already looking for character, checking if character, and character in this case is A, right? So I can write character here, which gonna be A. So if I check, if I put A in this condition, it's gonna access the key A, which it's gonna return the node, or like the value of this key, which is a node. So basically our node gonna be pointing here. I hope it's more clear. If not, just watch this video again, like this part. When I post it, it's gonna be more clear. Okay, so let's. Oops, my SkyDraw is bugged. Okay, you're welcome. Please, anyone also want to explain or something? Go ahead. So now we did F true, and we did node children, jar, or like character. Now we have node here. Now our pointer, the node pointer is become here, the node. Okay, what the point? Why we are doing all this? So because we want to check if all this character exists in this series, right? So what will be the next thing? If we move this, we need to move this too. But this gonna be controlled by this. So maybe we should stop here and let it loop, right? Yeah. So it's gonna loop. That's all we did. Which means this gonna move to P. Which means we're gonna check again for if character in node children. What is node in this case is not this one, it is this one. Now the children of this A gonna either find it. I'm gonna do the same. If I find it, that means I'm gonna move here, right? If I didn't find it, I'm gonna return false. That means the word doesn't exist. Okay, I keep looping again, P, I found it. I loop again. L. I found it. I loop again. The last character. I found it. Now this is the last character. Now
you have to check if the end has false or true, because you remember you had added a flag to it to make sure it's a word or a prefix.
Wait, can you repeat, please?
You added at the last character. You added a true in the insert method. So to differentiate between prefix and word. So this is a word. So you will have after the loop end, you will have to check the last node end to check if it's true, then return true. If it's false, it's a prefix. It's not true, so it's false. I think.
Okay. So here, when we reach to the end of the character, so we need to check, right? So it's gonna be where? Inside the loop? Outside the loop?
Outside the loop. Outside the loop.
Why outside loop?
Outside the loop, because outside the loop, we will, by the time we go outside the loop, we will be sure that we are at the end of the word. If not so,
the last node.
Okay, we finish looping on the character. So
yes, and it returned false because it finished looping because
okay.
Okay. So check if it's return. You either return true or false.
Okay, so basically if it's finished looping, that means my node is pointing in last node, and
yes.
So I can do if node.
Prefix or a word, Monsef. You wanna check if it's a prefix or a word.
So if node and is first, is true.
Yeah.
Is true.
If true, you return true.
Return true.
Else false.
Or we can do if, or like we can do return if prefix. How we can do that? Like we can do
return the node because it's already false or true in it.
Wait, because okay,
node,
wait.
Node dot end.
Okay, node.
But I don't know how to
I'm
actually.
confused.
You return the value in the end. You have a value in the end. If it could be true or it could be false. You just return this value.
So return node that end, because if it was true, that means we found the word.
Yeah.
If it was false, that means it doesn't exist.
It's a prefix.
Yeah, it's a prefix. It's like a prefix. So that means maybe Apple S.
Yes.
Not maybe we have this.
Yes.
Not this. So we actually didn't find Apple. Okay, I think this will work. That's really good. Nice. What else? Starts with. Okay, maybe I think starts with is the same thing. We just gonna
return
true.
You just reverse it.
Return true. It's gonna be return true here.
Returning a boolean to start with. Let's see.
It's return is the same thing, but it's not node dot end.
Not
yeah.
Okay.
Not
dot end.
Dot end.
If you return this, if you return this, if it was a word, you know a word is a prefix of itself. So if it was a word and you are returning the reverse, you are going to be returning false. Meanwhile, it was the word which was a prefix.
Yeah.
So
if that's the case, if it finished looping, you return it true.
Yeah, I think it should return true. By the way, if we did go fast in this part, let me repeat. So we did solve search, right? We in our mind it's working. Now the second method is starts with what it does is like it give it like, for example, A, B, right? And it go to the try and search. If it's found it doesn't care if it have mark or not. It doesn't care if it is a word or like or a prefix, like, because even if it was a word, it's prefix of itself, so it's gonna return true. But the search, someone might ask, okay, what's the difference between search and start with? The difference is the mark, because in search we're looking for a word, so we have to insert apple, all of it. If we have apples with s, it will not count. Now, so it is the same code, it's just gonna be here true instead of like return that, it's gonna be true. Because why true? If it is true, it means we did loop on all this character and we found them all. If we didn't find them, this was gonna happen, it's gonna return false here. So if we survive this loop, that means this all character we found them in the our linked list. Okay, let's start coding. This is gonna be fun. Okay, let's me copy this amazing pseudocode. I need to improve my pseudocode. Oh my god. Like the interviewer gonna be like, okay bro, I'm not understanding what you're doing here.
How are you going to initialize it first?
Okay, so we got this idea to create like a node like this. I'm sure it's possible to do it just with this init. I think this will make it more clean. To like create a node class, and then we just use this class to create a new node. Right? I think.
Yeah.
Okay, so let's split our case. Now we start from insert. Let me do this. Do this. Okay. Now let me zoom a bit.
The first thing is where the class is being initialized.
Okay, what that mean?
So at the initialize, that's where we call the node
root. We need to create root.
Yeah, self dot root or self dot node. Self dot root or self dot node, where we initialize the node class.
Okay. But are we sure that we need to create? Let's see what's happening here. So the call tree, it's create try. So at first it's gonna be our try empty. So yeah, so basically we're gonna call this node right here. Let's call it root. Self. That's root, and equal node.
Sorry.
Your voice cutting off.
A suggestion.
Wait, who is talking? Can you repeat?
She's trying to say something.
Me.
Yes, go ahead, please.
Yeah, I want to suggest something.
Yes, please, go ahead.
So, you know how we're trying to create another node? If while initializing the try, we create the dictionary and the end together there instead of putting the node.
Oh yeah, there is like two ways we can do. Like your idea is to create this right here inside it.
Yeah, instead of doing a separate node inside it.
Yeah, it's possible.
Then we just call try again.
Okay, let's try it here. We can do this. So let's remove this. So basically, instead of creating new node, we can use the same class that will.
Yes.
I think it makes sense. So let's use this way. I think false here. So, let's see. Now, wait, is it gonna be? I think it's gonna be fine, right? Because when he's gonna call try, it's gonna create this object with these children and it's empty. So when we're gonna insert on inside it.
when we try to insert, what are we going to insert? Are we going to insert
like
new dictionary? We are going to insert a new node.
Like not
a new
not self.
It will be another try again.
No. So we're gonna insert in self, which is this try.
Okay. Is that fair?
So
okay. A try contains tries. It's true.
Because now our node is itself, like this one, this try, this object. That's why I said like creating a node outside, it's remove this bit confusion. But same it's gonna work. Like instead of you gonna do self root, and then you have here self that's root that's node, right?
Okay.
And you have class div so like this is keep the code clean. Maybe we should keep it like this because it's more understand. What did we call that? Int? So this is our node. We initialize the root and we give it node. Now here I'm gonna insert node. So like this node is current in our case, current equal root is pointing to this root, right? Which this one is this one clear, guys? Do we keep working like this or we use the other one? The other one is confusing a bit. This one you understand that okay, this is a node, and now we initialize this tree, we create a node, and then we have pointer current on node. Current is pointing root like we did here. So we're gonna just follow the pseudocode. Current equal node, loop on each character. How we gonna do that? Loop on each character. 4? Is it 4? 4 car in word. Is it gonna work? Now we are looping
on self.word.
On self.word, okay. Self.word. Okay, now we are looping on each character. We are following our pseudocode. It's making sense. Now inside this check if character exists current, we're gonna create character node and add it to the current. So no, sorry. Check if character exists current children. So check that mean if character, okay, this check if character exists in current children. Current is this. If how do I check if it exists? So we know children is a hash table, which is mean dictionary. So we can do like if car exists is on. I forgot the keyword to check in hash table.
Can I use in?
Not in?
I think in.
In.
If car in.
If car in current children. Children, right? This is children. What I'm gonna do if I find it there, I'm gonna create character node and add it to the current.
If we find it there, then we don't need to create.
Oh, so this is an error.
Not, right?
Oh, check if car exists. Okay, so if not, okay, this is a pseudo or error. If it doesn't, okay, if it doesn't,
you can just if char not in.
Char not in. Not in. Okay, someone my last here is asking like, Why if it doesn't? Can someone explain that?
Because that's where you add it to the.
Because
if it's already there, you don't need to.
We don't need to create, right? Because like if we are like trying to add apple, and we have like other word that's up, so we don't wanna like add a here. A is already exists. You just need to traverse to the end and then add le.
And branch off.
Okay, so if jar or like if character not in current children, we create character node and add it to the current. Okay, how are we gonna create it? So to create it, we gonna use node, but we need to maybe current children car equal not like this.
Makes sense.
So if char not in the current children, so we are in the current children, which mean we're checking the hash table. If it doesn't exist in the hash table, we're gonna go to that hash table and we're gonna add it there. Now what we're gonna add? We're gonna add a node list.
Yeah.
Okay, let's keep going. What else? Add it to the current. Okay, we did add it. Current character node that we add. Current's gonna become character node that we added. So we're gonna move current. Current is not gonna become equal self root. So current's gonna be, but I think outside F. Right?
Outside of F.
Yeah, I think outside of F. So current's gonna become next one. Current children? Yeah.
The same thing, just copy plus C.
Oh, current children. Yeah, okay. So it's gonna be current children char. So this node itself, because we created. Now we didn't find it. We created. Now this root, this current was here. Now it's gonna move to here. So it moved to the one that we create, which is not. Okay, we're gonna do this current end after the loop end. So where's our loop end? It's end here. Current end. True. So basically we just copy paste the same pseudocode to here. We didn't change anything. So if you didn't understand,
Once if equal true, not true.
Yeah.
And true in Python had to be capital T.
Yeah. Okay. Thank you. Okay. So like if you didn't understand the code, just go back. Maybe if you're watching this recording to the part we were explaining the pseudocode, it will make more sense. So if someone have question, please go ahead. We can like explain the code.
Yes.
Part of the code.
I wanted to say.
Yes. What? Can you repeat?
Okay. So in a situation where the node exists, so in this case we are checking if the character exists in the hash table or hash map.
Yes.
So in a situation where it exists, we'll have to check all the children till we get to a point where it doesn't exist before we can add that node. With this instance one.
Okay, your voice is cutting off. Can you repeat the part?
Okay. So, can you hear me better?
Yes.
Okay.
Yes.
So what I'm saying is, we are checking in the hash map if the node exists. Or if the node doesn't exist. So if it doesn't exist, we add the node. We have already gotten that one. So in a situation where the node already exists, that means we have to check that node's own hash map to see if the next character is there. So what I'm looking at is this insert going to that.
Oh, so your question is this insert gonna work in case the word already exists in there?
Yes, where it exists.
We can try do simulation. We can try do simulation and see if it's gonna work. How are we gonna do that? We can do like let's say this is the root.
I can just go through. Okay, no problem. Go ahead.
So this is A. We already have like A pay. The hell is this? Okay, so this is the root. I don't know why the root is small. Right, and now I'm gonna insert Apple, right? Let's see what's gonna happen. Let's go to the current self root. It's for car and self word, which mean Apple. Let me write it, Apple. And it's gonna go on each character in Apple. So first time it's gonna be here. Okay, it's gonna check if car not in current children, which mean this is gonna be false. That means it's not gonna do this, right? And notice the current is pointing here.
Okay.
This is very important. Yeah. So let me group this. Now, this is become false. That didn't go here, right? Now it did current, move current to children of car, which we know that exists because if it didn't exist, it's gonna go here. But because it exists, we know that A is here, so this gonna move to here, right?
Okay.
Yeah, it's gonna loop again, which is mean gonna go to P. It's gonna go to P again. Gonna loop, gonna find it. It's gonna move here. It's gonna keep moving. It's gonna reach here. It's gonna be like, oh, L doesn't exist. P. What it's gonna do? This condition gonna be true, which means it's gonna go to the children of the P, and it creates a new character, which is character L, and it's gonna give in the value node. So node gonna be in here, node added value L, and yeah. So it's working.
Okay. It works fine.
Okay, let's see. Does anyone have a question? Let's see the search. So the search should be fine too, because now we are familiar with this amazing pseudocode. Insert, search. Okay, let me put this here just so I can see the pseudocode. Okay, how are we gonna do this? You can just start again, search. What is the first is not equal root. So to keep the code the same, we can do current, or it will not make sense, right? So not equal root, which means self root. Okay, loop on each character. Okay, so it is the same. Okay, here I am looping on each character. Check if the character in node children. Okay, I believe it's also the same, right? Check if character exists.
In this case,
not in. Because used not in.
Oh yeah, N. You're right. In this case, it's not gonna be in N because we are checking if it exists. If character in current children, if it's false, it's gonna return false. Now, in our case, we can do how we can do this if it's false. So if
you can keep if char not in. current to children, return false.
Not in. Okay. Not in.
No, not in, return false.
Okay, return false. Else.
You don't need an else because it's after return statement.
Oh. Okay, so
You can just
return. No,
not return. Not return. You keep looping. You keep going. What is the
Wait,
next?
we're not gonna do this?
You move the current. You move the current.
Node become node children. Car. Okay. I forgot why we did this. Because if it is true, it means it exists. I need to move, right? Because the point is to move on each character.
Now outside of the loop, you check the last.
Return true.
Not return.
Oh, so this is the
start with
node end. I believe we did, right? Not end.
Yes.
Return node end. Okay, and we said the same code gonna work for this.
Yes.
And we said instead of node end, we're gonna do true.
Yes.
Okay, let's see this if it's gonna work. Yes, please go ahead.
Please go back to the code. The method pointing towards none, and then the other one, which the search method pointing with an arrow key towards boolean, and then the other method, insert method, pointing towards none. I wanted to know, like, what's the essence of using the arrow key to point to those two objects?
Okay, someone here wanna explain this?
Okay, so in Python, that's like how you show what the return value of that function is. So for this search now, the return value is boolean. For insert, is not returning anything, like void for C, and then start with return C boolean type. So search will return true or false. Start with return true or false. Insert will just run; it won't return anything. So it's just a notation for the return type of function.
So basically, it's is like what he said clear? Did you understand?
Yeah,
so
thank you.
It will work if we remove them. It will work fine, but like to make like the code more clean, understand. It's also there is a command that check if there is an error in your code, and this help with that. So when we're writing our function, we know it should return boolean. So if there is something wrong in your code, and you check for, I forgot what it's called, it will give you error. Okay, where we were? True here. So basically this is our code. Let's run. Let's go. Let's see. Okay, I wasn't expecting it's gonna work from first time. Okay, try object has no attribute word. Where is this?
That's self.word.
Oh, okay. Okay, word.
Word.
Okay, word.
It should just be word, I think.
Just word. Okay. Word. Word.
It's actually local, so you just use word because it's local. It's a local variable.
Yeah, it's not like in here. Okay, let's run. Name current is not defined. In line 33.
Okay, you just copy that, pasted.
Oh, so
It's
no.
supposed to be node.
Yes. Okay. No worry. Wait, another one? Name word is not defined. Did you mean or? Which line is it? For each?
That's sweet. What's that?
Oh, start
there's
with
no
doesn't
word,
have.
it's
It's prefix. Okay. I don't think I'm gonna pass interview like this, guys. Come on, man. Give me a break. Name current is not defined. Okay.
It always happens.
Oh my god.
It's
Okay.
copy and paste problem.
There's no way you can write a program once and it will give you the
Instead
output
of
once.
current,
You must
no.
have errors.
Okay. Which one it should be here?
Just
Instead of current, node.
Node. Oh yeah, node here.
Yeah, it should be node.
Oh my god.
It's perfect that. Okay, yeah.
Node. Okay.
Yeah,
Okay, let me
that's
check
true.
if there is more, because if it show me one more error, I'm gonna punch this monitor. Okay, run. Come on, man.
Who's judging?
Oh, let's go. Good job, guys. All green. Nice, nice, nice,
Submit it,
nice.
Monsef.
Nice. Well done, guys.
Submit
Well
it,
done.
Monsef. Submit it, Monsef.
Let's submit.
Nice.
Congratulations.
Oh, okay. Not bad. Not bad. Okay, good job. I hope if someone have confusing, just watch recording. It will be more clear. And thank you everyone for this amazing session. Now we understand try very well. And congratulations for completing 3
Someone
weeks.
said at the beginning of the recording, this is going to be an easy topic.
Can you repeat?
Monsef, did you not say at the beginning of this it's going to be an easy topic?
Yes, I said, but it's not that easy, I guess. Yeah. Like,
Sorry, please. What was the next topic, please?
so the next topic is the Tuesday of next week is gonna be about interval. Interval.
What's that?
I don't know.
Oh, you haven't. Okay.
Something.
Merge intervals. Oh, this should be
Yeah.
interesting.
Interval is quite interesting. It's quite a good topic.
Yeah.
It's
So
nice.
interval, we're gonna see next week dynamic programming, binary, math, geometry. If someone wanna help with this math and geometry, please go ahead. Or anything here. Good sound. And the week 5 is gonna be all Let's Code. So the 4 week is all about like understanding this topic, but week 5 we're gonna start Let's Code. Maybe do like a tournament, see who is the first one gonna solve some Let's Code. Maybe better score like here, like beat 70% or wherever.
Okay, so we're done with the data structures after the intervals.
After the week 4, the next week, we are done with the topics. It's gonna become like these topics that we learn, we're gonna use them in the next weeks to keep solving.
Okay, so we have all the ammo after week 4.
Yeah, and congratulations everyone for like passing this 3 week. It's really hard, but
Thank you so much.
you guys
Thanks,
doing
guys.
good. Let's keep going. Have a good night. See you next week. I love you all. Okay, let's keep going, guys.
Thank you, Munsif. Thank you,
brother.
guys.
Thank you, everyone. Okay, I sent the code. Yeah.